Welcome to Quant Platform Overview and Data Processor for Finance 372. The Quant Platform is a tool that we'll use to conduct backtests and analyze the results for different trading strategies. The platform will have 5 main components. The first is a data processor that loads and merges the data we'll use for the backtest. The second is a portfolio, which keeps track of the current portfolio and the balance sheet for the account. It also keeps records of all the trades you've done as part of the strategy and keeps a history of the account's net asset value and margin requirements. The third component is a trading rule, which decides which trades to make given what the data processor is telling us about the current data and what the portfolio is telling us about the current portfolio. The fourth component is an executor that takes the desired trades and executes them. For our backtests, this executor will be what accounts for any kind of liquidity costs we want to assume associated with trading. One of the nice things about the way we're designing this platform is it's easily adaptable to live trading, where part of that adaptation would be to use a different executor that submitted the orders to some API or live trading platform. Finally, we have a statistician component that computes means, standard deviations, Sharpe ratios, and other performance statistics that we've talked about in the course. So the big picture for what this platform does every time we want to backtest is as follows. First, it tells the data processor to load and merge all the data we're going to need. Second, it loops through a list of all of the relevant dates for the strategy. For each of these dates, it's going to get signal and price data from the data processor. The difference being that the signal data is what we're going to use to decide what to trade next. The price data, we're going to use that to update the prices what's currently in our portfolio. Next, we're going to tell the portfolio object to update our current portfolio's value and prices. Then we're going to ask the trading rule to decide which trades to make based on the updated portfolio and the signal data frame coming out of the data processor. Fourth, we're going to tell the executor to execute the trades. And then finally, we're going to update the portfolio again to reflect the newly executed trades. We loop through this. We do this every day or every month or every year in our historical sample. And we build up an accumulation of how does this trading strategy do historically. Finally, once that loop is complete, we can ask the statistician to summarize the results. Going forward, I'll have one video for each of these major components, beginning with the data processor, which we'll cover today. So how do we code up a data processor? Well, we're going to write this as a class. And the reason we're going to do that is because we want to make this interchangeable and replaceable. So I can write one data processor for a book-to-market strategy, the value strategy. I can write another data processor for a carry trade strategy in currencies. I can write another data processor for some volatility strategy in options markets. And I can swap them out while keeping the same code for our portfolio manager, the same code for our statistician, and the same code for our main backtest loop. Okay, so how we're going to do this is we're going to make sure that even if you're using very different strategies, the data processor class that you write has functions with the same names. Okay, and there are going to be 4 key functions here, which we're going to write today. The first is a constructor, which is called when we create the class. Inside the constructor, we want to load and merge all the data we're going to need going forward. So anything that requires gathering data from a CSV file or using a web request to download some data, whatever it is you're doing to collect data, we want to do that once at the beginning when we construct our data processor. The second function we need is a unique dates method that returns an array containing all of the different dates we want to do the backtest on. Because remember, in our pseudocode we have above, we're going to be doing a for loop through all the different dates. So we need a way to get the list of dates. The third function we need gives us a signal data frame for a given date. So the signal data frame can only give us data that was already available as of that date, because this is what we're going to use to form our trading strategy. The fourth function returns the price data frame for a given date. The price data frame is different because it only focuses on the prices of the securities we're trading, not the signals. And it's also different because it's going to cover a bigger universe. The signal data frame should only return rows for observations we might actually trade on that are in our trading universe today. The price data frame is going to return prices for a broader universe we might actually not want to open up new positions in today, but we may already have positions from 2 months ago or 2 years ago that we want to update the prices for. All right, let's get started with some code. To start, we'll import a few different libraries we're going to use, and now we can define the data processor class. And we'll call this one a BM, as in book-to-market data processor, because for our example, we're just going to be loading data for a simple book-to-market strategy. Okay, so you can see to start here, I've just defined a simple class called a BM data processor with a constructor that all it does is prints BM data processor created. So this is just our starting point to know that we were creating this class correctly. To test this, let's create a BM data processor. Okay, so if we run this cell, what we get is our nice message saying that the BM data processor was created. The first thing we need to do inside of this constructor is to load the necessary data. So I've included with this video some data files we're going to use, and you can put them in any folder you want. We just need to put the path to that folder in a variable right here. So in my case, I have a folder in my D drive called fin372/data, and that's where I store all the CSV files for the course. We can also have a relative path here, so if you have a data subfolder in the same folder as this code file, you can write that like this. All right, so now that we have our path set up, we can load our price data. The price data is in the file called monthlyreturns.csv. What's in this file is a monthly sample from 61 through 19 and includes all public US equities. Now we can load the data using the pd pandas.readcsv command we've talked about before. We can put in the data folder path, and then within that path, we tell it to look for the monthly returns.csv file. All right, and whatever comes out of this read CSV, we're going to store that into the price data frame that's going to live inside this data processor class. Okay, so now in our test, we can create a data processor class, and we can ask to see what that price data frame looks like. So you can see we've loaded a data frame with 4 million rows, 7 columns. The columns are permno, which is an identifier for the stock, date, price, volume, return, shares outstanding, and return excluding dividends. That's what the red X stands for. So we notice a couple things right away with the data we've loaded. The first is that this date column is a number and not a date time 64 value. We can see that more clearly if we ask it for the D types. We get that the date is an integer. Another problem you'll notice with this data frame is that the prices can sometimes be negative in here. If you do some Googling, you can read about why CRISP does this. Normally the price here reflects the price from a closing auction, so it's the single close price. Sometimes those auctions, though, don't have any volume in them for small stocks. And so what it does instead then is it uses the midpoint of the bid and the ask price as of the close, and it indicates those midpoints with the negative sign. For our purposes, though, we'll just ignore that information and take an absolute value of that. The two changes we need to make to our constructor here, first, we need to parse those dates into date times 64 variables. So the way we're going to do that is using the pandas.toDateTime command, and then we're going to tell toDateTime that the format of our date matches this code right here. If you want to learn more about these different formatting codes, I provided a link in the comment right here. Okay, so if we run this modified version here, you can see that the dates now are date times 64 instead of integers. The second correction we need to make is we need to change all of the prices to their own absolute values so that they're always positive. So we set the price column to be equal to the absolute value of the current price column. We run this, and we see we have correct date column and a correct price column. Next up, we need to load our signal data. For this strategy, the signal that we want to use is the book to market ratio. We need to get book values of equity from accounting data to measure that signal. Our sample is from 1961 through 2020, and it's in a file called compbm.dta. These .dta files are data files, and they often do a better job than CSV files of remembering your data types. The command for reading these files is pd.readsdata, and then we put in the same path and then the name compbm.dta. So for this to work, we need to make sure that the monthly returns and the compbm files are both in the same folder. Now we can run our test to see what the signal data frame looks like. You can see it gives us 1.6 million observations. The reason it's fewer is these are quarterly data instead of monthly. We have a GV key, which is an identifier for the firm. Data date, this is when the fiscal quarter ended, so that's why they're always at the end of a month here. The fiscal year quarter, the fiscal quarter. RDQ, this variable is important. This is the release date of quarterly earnings. So this is the date on which they made the announcement publicly. To see how many rows we have where we actually know what the release date of quarterly earnings is, we can use this command here. We can ask the data processor for its signal data frame, and we can ask each one whether it's an NaN or not, and then sum will just add all those up. Since there's not NA, it turns everything into a 1 if it is not an NA, 0 if it is an NA. Summing this up like this will just count the numbers that are not NA. So we run this, you can see that we have every observation for GV key, data date, fiscal year, fiscal quarter. We have a little more than 1 million observations for the release date of the quarterly earnings. And the other variables we have, pretty good coverage, even though a lot of them look like NANs right here. So what are these other variables? CEQQ is common equity. These are the book values. CShowQ is common shares outstanding. SEQQ is the shareholders' equity. And then this is the price per share. Okay, so SEQQ and CEQQ are both book values. We use that as our numerator for book to market, one or the other. And then as our denominator, we'll use common shares outstanding times price. If you go back to look at this data, you might notice we have a problem here, which is that the identifier for firms in this sample, in the signal data frame, is the GV key, but the identifier for firms in the price data was called PermNo. So we have two different identifiers. This is going to be a problem all the time when you're trying to merge two different data sets together. Different data sources use different identifiers. Sometimes it's ticker, sometimes it's QSIP, sometimes it's PermNo, sometimes it's GV key. The good news is we have these intermediate databases that let us convert these identifiers from one to another. Okay, so in this case, we need a converter that takes these GV keys and makes them into PermNos, or vice versa. In this case, I provided a GV key to PermNo converter. So we can load that here. It's another Stata file. It's in GV key PermNo conversion.dta. To see what this thing looks like, we can now ask our test to print out the converter instead. And you can see it's very simple. It just gives us GV key PermNo for a given date. The reason we need the dates here is because some of these things change over time. So there's not always a permanent one-for-one match between GV keys and PermNos. It's a date-specific match, so that's why we need this. All right, we're not interested in the converter for its own sake. We're interested in adding it to the signal data frame, so now we can easily merge that with the price data frame. The way we do that is with a command like this, where we set the signal data frame to equal the current signal data frame merged with this converter. And we want to match rows where both the GV key, which remember that's the identifier we have right now in the signal data frame, and the data date match what's in the converter. And then we're just going to add this PermNo column. Okay, you can see now with this command, if we go back to showing our signal data frame and run this, now we have a signal data frame with GV keys and PermNos all across the board. Finally, I'm just going to clean this up a little bit. And then I'll put in a permanent test here where I can make sure if I ever go back and modify a little bit what's going on in my data processor, that this initial constructor works and loads a price data frame and signal data frame that looks like we want it to look. Okay, so with these tests in place, what you'll see every time you run this is a printed version of both data frames. So if you ever go back and modify using a different data set or different column variables, you want to make sure when you run this, you get data frames that come out and they look like they're supposed to look for your specific application. Next step is to write this unique dates function. What this function does is it returns an array containing all of the different unique months in this book to market sample. Okay, and we don't want to just return every single month. We only want to return months where we still have some of both the signal data and the price data. So to start with, let's define the function outside of the class, and then we can insert it in later once it's all up and running. Okay, so we'll call it unique dates, and for now we'll have it be a function of a data processor. Once we put this in the class, this will change to just be self. For now it's data processor. And to start with, let's just do something very simple where we'll take what's in the data processor, grab the price data frame, and return just all of the unique values of that date column. So what happens when we do this is we get an array. That's good, we want an array. But it's not in order. You can see that down here it jumps back to 1960s. And it's also including stuff where we may not necessarily have signal data. Fixing it being out of order is pretty simple. We can just do np.sort. If we run that, we get sorted version of this. That's good. Next, we want to filter this array of dates so that it only contains dates where we should have data from the signal data frame to actually do some trading. First, we'll make that a little bit easier by making this into a series instead of an array. We'll call that a series price dates because these are the dates that we have prices. And we'll use the pd.series command to change that over into a series. So if for now we just return the price dates, you can see we now have a series. So that's good, but we want to make sure that these date times are greater than or equal to the smallest date on which we should have some signal data. So what do I mean by that? All right, so first let's figure out what the smallest date we have for signal data is. Call that the min signal date. And we'll use the RDQ column to measure the release date of these information. Now, in practice, you're not able to immediately trade on information the minute it's released. These book values of equity are not in the bottom line earnings number that come out over the newswire, and you can immediately use them the next day. In practice, it can take a couple weeks, even today, to get that data released. Companies take a while to release it. Your data vendor takes a while to process it. So we're going to just be careful here and add 30 calendar days between the release date of the quarterly earnings and when we're allowed to trade on it. To add 30 days to this date, we use the time delta function, numpy.timedelta 64, 30 days. Okay, so that's our min signal date. Let's for now just print that. And you can see that the min signal date is sometime in the middle of 71. Okay, so all of this stuff we have in the 1960s, we can't really use that for a book-to-market strategy if we're assuming you need to wait for these RDQ dates to come into the data set because they're not really there before 1971. Okay, and then when we add 30 dates from the smallest RDQ date, we need to at least wait till this point here. So how do we do that? Well, instead of returning all of the price dates, we return price dates where they are bigger than the minimum signal date. We look at that. Now we have a series starting with the 1971 date. Okay, in principle, we can keep using the signal information many years later. So for example, our signal information here ends in 2020. In principle, you could still be trading on that in 2030, but maybe we also want to have a maximum where we're not using the stalest data there is. So let's just write the max signal date now as the biggest RDQ. And then let's add, let's say, 365 days to that. So we only want to use information that was released in the prior year. Okay, we can do that, add that to this condition here using an AND. We make sure that the price dates are less than the max signal date. All right, doesn't have an effect here, but if we had a different time frame, it would have an effect. Okay, we're almost done here, but remember we were hoping to get an array. The problem with this series is it has these indices attached to them, and so it's going to be a little confusing to work with going forward. So let's just make it an array by doing array here at the end. So now we have a date time array, and we can just loop through this very easily. Now that we've got that working, we can add it into our class here. Let's paste what we had from before, and then we can copy this function over. And the only thing we need to change here is instead of data processor as the name of the argument, we need to say it's self, because we want this to be a function of the class instead of an independent function. And then everywhere inside the function that says data processor, we just need to change that to self as well. Okay, and then finally we can add a test here to make sure that this is working. Now if we run this cell, we should see the price data frame, the signal data frame, and now our array of unique dates. Our next job is to write a function that returns the price data frame for a given date. So this one's going to be pretty easy because all we need to do is return all of the available price data in the date that we pass to the function. This is simple enough that I'm just going to write this straight into the class here. So I pasted what we had before. So now let's add a new function here to this class, price df for date. And we'll pass this function a date on which we want to return all of the price data. So let's start by just returning right away the price data frame, but not all of the rows of the price data frame, only the rows with matching date to the date that's passed to this function. Only the rows whose date value matches the date that we pass to this function. Let's test this out. We'll pull out an array of unique dates. We'll grab the 60th date just as a random date to test, and we'll ask for the price data on that date. And you can see what comes out here is a price data frame with 5,000 rows. There's a lot of prices available on this date, 1976. Everything looks pretty good here. The only thing we're going to want to change, though, is that this column permno, that's our identifier for the security here. And we're going to want to be a little bit more generic with that name. The idea is that when we use this Quant platform, we don't want the other components to care that whether you're using permnos or tickers or GV keys or anything else as your security identifiers. So we're just going to change that to be called a generic security ID column. And then anything that uses this price data frame doesn't need to know whether it was a permno or a ticker or what. It can just use that security ID column name and know that whatever's in there represents our identifier. So to make that change, we just need one simple extra line of code here. We'll call this price df for date, and then we'll just modify that a little bit before we return it. The only modification we need is to change the name of that one column. We do that by renaming columns. Permno becomes security ID. Okay, so if we run this again, we now have that column renamed to security ID. Our last job here is to create the function that returns a signal data frame for a given date instead of the price data frame. The difference here is that we're going to be returning the signals we use for the trading strategy, in this case, the book value of equity and the market value of equity. And then we're also going to filter here a little bit more, where we're not going to just return every observation we have. We're going to look at only the universe that we might want to open a new position in. In this example I'll show you now, we're going to only return stocks that have a share price above 3. That'll be our liquidity filter. This one's going to be a little more complicated, so let's write this function outside of the class as we did before. We will define a signal df for date function that takes a data processor and a date and returns the signal data frame for that date. So our starting point here is going to be the price data frame because we only want to be considering stocks to trade that have prices available today. So as we did before, we can get the price data frame for this date by grabbing from the price data frame column that includes everything, only the rows where the column date equals the date that we passed in here. Okay, now just to see how this works, let's return the price df for date and test it here. We already have a data processor created above, so we can just do signal df for date and then pass a unique date, just random one, the 60 is fine. And then we can run that cell and this cell and see what we're getting back is just the same thing we already know, the price data frame for that date. Now we want to filter this a little bit. The first problem here is you can see that sometimes the return values are NAN. All right, and so we don't want to accidentally buy a stock or trade a stock where the next period we don't know what the return is or the price is. All right, so to do this, we need to make sure that the next return is always available before we allow an observation into our universe for trading. One way we could do this is to every single time someone asks for a signal data frame, we could calculate the next returns and filter it out. But I'm actually going to make this a little bit easier, I think, by going back to our constructor that we made at the very beginning. So let's copy this cell that has our class definition in it, paste that here, and then we're going to modify it a little bit. We're going to add another column to our price data frame that we're always keeping track of, the full sample price data frame. Let's add an extra column to that, which is the next period's return. The way we compute that column is using this function I wrote called safe lead lag. The idea here is that you could imagine just simply taking the next return observation by going one row down in the data frame and using that as the next return column in this row. And that generally works, right? If I have, an observation for Facebook in January and then an observation for Facebook in February below it, if I want to get the next return as of January, well, that is the February return, one row below. Okay, but the problem is that the way this data frame is set up is we have all the Facebook observations, but then right after that we have all of the ExxonMobil observations and all of the observations for another stock after that. And so sometimes if you go one row ahead, you'll accidentally get a stock return that's from a different company, and you don't want to do that. All right, and so this safe lead lag function, this gives you a lead or a lag, as in an observation for some column ahead or behind the current row, but it does it in a safe way by checking to make sure that the company ID or the permno or the security ID or whatever you pass it stays the same. So we only give you the next observation if the permno is also the same, so we have the same company. If the permnos are different, we just write in NAN. Okay, I'm not going to go through in detail how this function works. It's sort of a very general function, but it should be pretty easy to use. I wrote some documentation here about how to use it. And you can see, for example, right here, the first argument here is the column which I want to get the lead and lag of. The second column is the column I want to check to make sure it stays the same. So we don't want to cross over into a different permno. And then the third column, 1, this just means the lead or lag is 1. Okay, so if I want this to be even clearer, I can write it this way. Data series equals this. The first argument is the data series. The group series is the second argument. Groups are what we want to stay the same across leads and lags. And then the lead lag is 1. The way I wrote this function, a positive lead lag gets you into the future. A negative lead lag gets you into the past. And you can see what I get down here is that my price data frame now has another column, which is the next return. And you can see for this first observation, the next return is this row. For this observation, the next return goes down to this row, et cetera, et cetera, et cetera. Okay, so now that we have that, we can go back to this function and filter this price data frame, only grabbing the columns where we actually have returns for the next period. We'll do that by locating observations where the next column is available. And the way we'll check to make sure it's available is we'll do numpy.isFinite. So isFinite checks that what you pass it is both not an NaN, so it's not an NaN, it is a number, and it's not infinite. Because if we had an infinite return by some data mistake, for example, that would also be bad. We wouldn't want to use that data. Okay, and then we want all of the columns in those matching rows. Okay, so if we rerun this cell and this cell, what you get here now is fewer observations, and because we're missing all the ones that are missing that retnext column. So retnext is defined and available for all of these observations. Okay, now that we've added the retnext column in here, though, we don't want that to pollute our future results. And so now that we've filtered on that, let's just go ahead and remove it right away, just so we don't accidentally use that going forward. And we do that using this drop command. So running that again, you can see we have the same filter down to 4,900 observations, but we don't have that data, which could accidentally allow us to cheat later. Now it's time to filter out the signal data frame. The first and most important thing is to grab only observations that were before the date that was passed in. We want to include only information that investors could have reasonably have known at the time. Because the signal data frame is quarterly, we're not going to be able to match exactly this date. So what instead we're going to do is we're going to start by just getting all of the past signal data frame. So everything that was, even if it was 10 years before, we'll grab everything in the past. The way we'll do that is we'll grab we'll locate in the signal data frame anything with a release date of the quarterly earnings, RDQ, that is less than or equal to the date. But we're going to also shift that date back 30 days. Because remember, we were thinking that there should be some lag between the release of quarterly earnings and when we can use it in our investments. Okay, so let's now, just so we can see what this looks like, let's return that. And you can see that we're getting a big data frame here now, 4,200 rows. We're not getting anything past the middle of 76, which is when this unique date occurs. All right, now one more change we're going to make is, let's imagine we want to change this 30 days to a different number. The way it's written right now, you'd have to go find it here, and you'd also have to find it in this spot up here where we used it to find the unique date, the minimum unique date. So let's change that in both places now to be a variable name. Let's have it be self.accountinglag, and then we could put that up top here as a variable you choose when you set up the class. And then we can do the same thing with the maximum lag. Remember, this is where we only want to use information at most 365 days old. So we'll call that max accounting lag. And we'll add that up here as well. Okay, and then we can rerun this cell here. And when we go to this definition here, we can change this 30 days to data processor dot accounting lag. We also want to make sure that these observations occur within at most a year of the past date. So we can do that with a similar filter here, but modified to make sure that the release date of quarterly earnings is greater than or equal to the past date minus the max accounting lag. Now let's grab the last observation only for each perm no. This will give us sort of the most recent information we have for each company. We'll call that the latest signal, df. And Python makes this easy because we can just group by perm node and take the last one only. All right, so let's see what that looks like. Can run this and this. And then we get only 2,500 rows here because this is only the most recent observation for each perm node. You can see that in some cases it's in June of 76. Sometimes it's a little earlier in March because we haven't had the June announcement yet. Okay, very good. Now the last thing we need to do to finish this off is just merge the price data back with the signal data to make sure that we have both price and signal information, which we need. We do that by starting with the price data frame for each date and merging in the latest signal data frame, matching on the perm no column, and we're good to go. Okay, and then like before, we want to rename the column perm no to security ID so that the signal data frame we return has a security ID column that other functions and other classes can recognize. To see what this looks like now, let's return the merged data frame, run these two, and now we get this big signal data frame that has everything we want in it, both the price data here and the accounting data that we'll use for our signal here. So if we to compute the book to market ratio now, we just need to use these common equity column and the shares outstanding and price columns. So now we can compute the book to market ratio using these variables and do any kind of price signals we want using these variables. All right, the last step here is we may want to do some kind of liquidity filter. Liquidity filter says some of these 2,500 stocks may just not be liquid enough for us to trade them. So I'm going to write that into a separate function. We'll call that here. We'll call that a liquidity filter function. And that's going to be inside of this data processor. And what it's going to do is it's going to take a data frame like this and just filter out by some liquidity rules. In this case, we're just going to make a simple one based on prices. So we can add that function right in here. All it does is it takes a past data frame and it returns only observations where the price column is greater than 3. We can rerun now our class definition that has this liquidity filter function. And then now our function here, signal data frame for date, will only return 2,100 observations because we've removed the ones that have prices less than 3. Okay, we're done. We can then copy this thing back into the main class definition and then change all the data processors to self. Then we'll add a big comment up here explaining what this function does. And then finally, we can add some tests here to the bottom to make sure this thing is still working. And then when we run this big cell here, we get at the bottom, our test results come out. They show the data frame containing all the price information, data frame containing all the signal information, unique dates, and we get the price data frame for just this date and the signal data frame for just this date. Price data frame has 5,200 observations, signal data frame 2,100. Okay, now this data processor is ready to go. We can use this to load data on a date-by-date basis and run our backtest. We'll see more about the role this particular class plays in the bigger backtests in later videos.